Okay, we'll go ahead and get started. This is the third day of the lecture series on research design, looking at options beyond randomized controlled trials. Before we get started, I want to send out a shout out of thanks to OU-Tulsa College of Arts and Sciences, Associate Dean Hellman, for helping sponsor the event, and Shelley Fowler, who's also helped coordinating the event and arrange the food, things like that. And also, of course, the OU-Tulsa Vice President for Research, Kent Teague, who's also contributed to sponsoring the event. So without them, this would not be running so smoothly. So this is the third day of this series. We talked on the first day about non-randomized designs, and then yesterday sampling strategies, and today we'll finish up the conversation by talking about matching techniques for balanced designs, that is, designs like observational studies, for example, non-randomized designs when experimental randomized control trials are not an option or are not feasible. So in general, the guiding questions for today's talk really have to do with these matching methods. What are they? What are matching methods? Why do we use matching methods? And how do we use them? Right? So the bottom line really is, I talked about using propensity scores, which I will mention some today, but the bottom line, I guess, takeaway is you shouldn't really do propensity score matching for these types of designs. A lot of the talk today is influenced pretty heavily by a recent paper just was published this year by Rich Nielsen from MIT and Gary King from Harvard, who wrote a paper on this topic. You can find the paper online. I think you can Google search it and get the full text PDF. The title of their paper is "Why Propensity Scores Should Not Be Used for Matching," and I think Gary King, if I remember right, is a political scientist, and I'm not sure what the background is for Rich Nielsen, but they will walk you through the intricate details of propensity scores and the statistical ramifications of using propensity scores for matching. And so I'll allude to that a little bit. I'm not going to get really deep into the weeds, and we don't really have time to do that in the 1 hour lecture, but that's what's pretty heavily influenced the talk today. Okay, so let's start in here with a scholarly influence on propensity score matching. So it's probably the most commonly used matching method by far. If you Google Scholar propensity score matching, it's something like 49,600 articles there, although I'm not quite sure about that metric, because over time the number goes up and sometimes it goes down, so I don't really know what it is. So I think maybe instead of 49,600, they should just say that it's a lot, right? In any event, matching is an increasingly popular method for pre-processing data to improve causal inferences in observational data. The goal of matching is to reduce imbalance in the empirical distribution of the pretreatment confounding variables between the treated and control groups, right? And Judea Pearl, who I mentioned in the first lecture, wrote a paper in 2010 that calls propensity scores one of the most developed and popular strategies for causal analysis in observational studies. The matching techniques in general, not specifically propensity scores, but the matching can be very effective for lowering imbalance, reduces some of the problems that we have with model dependence in the statistical estimation of causal effects, and as a result, reduces some of the inefficiency and bias that we sometimes see in these non-randomized studies. So generally speaking, we can think of matching techniques, not propensity scores in particular, but matching in general, because there are other ways of doing it. Right? We can think of matching as a technique for finding ideal experimental data that are hidden within the observational data sets, right? So that's kind of where we're going with this. So the resulting process of matching amounts to searching your data, search for a data set that might have resulted from a randomized experiment, but it's hidden within this observational, non-randomized data. And when done properly, then the matching can reveal these kind of hidden experiments. Many of the problems of observational data analysis go away. Okay, so we have to think about then, that's all great and fine, but if the goal of matching is to reduce this imbalance, well, what does that mean? What is imbalance? And if lowering the imbalance reduces the degree of model dependence, what do we mean by model dependence? Why is that important, right? It may be important conceptually to understand what those terms mean to better understand the whole process of matching and the benefits of matching, and why propensity score matching may not be the best way to go about it. Propensity scores can be used for a lot of things, a lot of other kinds of matching. It's about matching as used in practice as a data analyst. So other uses of propensity scores might include things like regression adjustment or inverse weighting stratification, if you're familiar with those techniques. Propensity scores can be used inside other methods, or even just the mathematical theorems about propensity scores. So all of which are correct. Propensity scores, as it turns out, have a lot of terrific uses. Matching just happens to not be one of them, right? And that's what I'm going to talk about a little bit today. So what is this issue on model dependence, right? We kind of bring the conversation along by talking about some of the fundamental issues around that. So this is an example. I want to convey to you what model dependence is with a graph. This is from another study. The citations there, Ho, Ma, King, and Stewart, 2007. This is a figure from their study that was published in 2007 in this journal Political Analysis. And so on the horizontal axis here, what we have is education, right? Which is just a control variable. And the vertical axis is some outcome variable, conveniently labeled outcome. And then the causal variable is the treatment unit versus the control unit. So that's the T's in the graph there, and the controls are the C's, if you can make those out. And so the goal is to figure out the effect of that binary causal variable, just a simple binary model here, on the outcome, holding constant education. Okay, that's the idea. And so how would we normally do that? Well, normally we would run regression on the outcome, on the binary outcome variable. That's the key causal variable that we want to know the effect of. So that's the C's, the control variables, versus the T's and controlling for education. If you run that regression, then this is what you get, right? If you run just a linear regression model, this is what you get. You get the straight line, which jumps up only for the causal effects. So what's the causal effect? It goes from control, the blue line, up to the treatment, which is the red line, right? So the effect is positive. That's basically what you get if you run the linear regression model. Now, let's suppose that's a problem because you actually expected it to be negative, right? You actually expected it to go the other way, so the results or the findings are kind of contrary to what you anticipated. So what do? What is a data analyst to do in this kind of situation? Well, one thing you do is you can say, well, notice that it doesn't really fit very well. It doesn't fit the data. The model doesn't really fit the data very well. And so maybe we should have made it a quadratic term instead of a linear term, right? Because the data, if you look at just the scatter plot of the data, ignore the arches here for a second. That's the next slide, right? But the data aren't necessarily in the linear pattern. So maybe we've we've tried to force a linear model onto nonlinear data. We've got model misspecification, right? So that happens sometimes, right? So we realize that maybe we should have made it a quadratic term. So now we run a regression of the outcome variable on the treatment versus control as our main causal binary variable, education, as we did before, but we we look at education as a squared variable, right? We make it a quadratic model, right? So then what happens now? Well, so now the causal effect, instead of going from control, the blue, up to the treatment as it did before, you can see the quadratic here, it goes from the blue down to the red, right? Same data. We just changed the model from linear to quadratic, right? Same data, just different model to fit those data. So now the causal effect is negative. And so, being completely sarcastic, right, this is very convenient for the data analyst, because now you can choose the effect, the causal effect, just by choosing the specification of the model, right? If you run a linear model, right, you say, well, it's a negative effect, right? But if you re-specify the model and make it a quadratic model, then it completely changes the interpretation of the findings. That's model dependence, right? The model depends on the researcher's prerogative of how we specify the model, right? And so this is how we get criticized as data analysts sometimes for, lying with statistics, right? Because we choose the models that we apply toward the data. Okay, so obviously this is a huge problem, right? This is the definition of model dependence. Small changes in the specification can produce big changes in the substantive results. And this is just a vivid example of this, but you all know how that happens. After you've done collecting your data and typing it all in and you're getting it all ready and you're in your office or you're in your living room and you got that one line over your head and you're, cranking away over the thing. You got the door closed, you run your analysis. You've been working on the project for 2 years or whatever. Are you done running the analysis? No, of course not. You keep doing things. You try things out and you see, what can we find? You delete outliers. You do all kinds of things. So model dependence is the variation in your causal effects across all of those results. And that's a really big problem. Okay, so let's see what we can do about that. So one of the things that we can do about that is we go back to the data set and we run matching, right? And what's matching? It's basically pruning, right? What's pruning? Well, pruning just deletes some of the observations, right? Perhaps matching, I think maybe matching should have been called pruning, because that's really what it is. You're just eliminating some of the observations that you don't need, right? But in a very specific way. It's not just arbitrarily picking things to throw out. In this case, it deletes some of these control units. So you see that they're kind of shaded out here. Some of the control units that are maybe outliers, so to speak, or they don't have treatments with scores that are a good match, right? We prune those out of the data set so we have more consistency between the treatments and the controls. Because remember, in a randomized experiment, we've randomly assigned participants to different groups so that we can ensure that we have matches between treatment and control participants. That they're homogeneous groups in every way possible except for the treatment that's been administered. Well, in a non-randomized study, we don't have that, right? So we've got controls that are out here that don't really have matches in the treatment group. It's a non-equivalent control group design, right? So what matching does is it allows us to prune out those controls that are non-equivalent to the treatment, right? And so we can more accurately compare treatments to controls that are similar, right? So we delete those control units, it prunes those off, and you can rerun that same linear regression or whatever statistical technique modeling that you did, and this is what you get. So now the linear regression shows that there's basically no causal effect, right? None at all, because we've pruned out those control cases, control variables, cases that didn't have matches, right? So now there's no causal effect because the blue line is almost right on top of the red line, and there's not much of a shift from one to the other, or red lines on top of the blue line, however you want to layer it, right? Well, the key point here is to suppose that we run the quadratic, which it turns out is also plotted already on the previous graph without having to click on anything, and you can see that the causal effects for the quadratic, if I go back to the previous one, was almost the same. The lines are pretty close together, right? It's probably not a statistically significant difference there. Okay, fundamental point here is that it doesn't really matter in the match data whether you run the analysis based on using the linear regression or the quadratic, right? After the match, because we've done the pruning, we could run the linear regression and we still get the same finding as we did when we ran the quadratic, right? The difference is we've pruned out those control cases, right? You get the same results regardless after matching as you do before. So the point here, just to kind of drive it home, is that before matching, model misspecification was a problem, right? Because if we run a linear model, we get one interpretation, one set of findings. If we run a quadratic model on the same data, right, without the pruning, without the matching, we interpret those results differently, different findings, right? After the matching, we get the same results either way, right? No difference between the groups. So the matching reduces or eliminates that imbalance, that model dependence and that imbalance. Okay, so let's maybe be a little more specific then. So what are the problems that matching solves? Well, without matching, you have that imbalance. So what is that? Well, that's when you have an analysis where, let's say, the binary variable is maybe some medicine where we're going to give to medicine that we're going to give to people, and you happen to give the medicine just to the healthy people and you don't give the medicine to the unhealthy people. Okay, obviously that's a huge control variable, right? So how healthy they are, if the outcome is longevity or something like that, and so you really want to pay attention to that. So imbalance is what matching is trying to get rid of. It's trying to get rid of the control variables, or in particular the relationship between the control variables and the key causal variables, the treatment variables. So what does imbalance do? Imbalance is the source of model dependence, right? That's what you see here. Without matching, the imbalance is the source of model dependence. When there's a balance, that means that, when there's imbalance rather, that means if you specify the regression or whatever model you're going to run to estimate your causal effects in different ways, you'll get different answers, right? You'll get different results. That's the model in dependence. So what does that do? That leads to researcher discretion, right? If we have that imbalance where you have model dependence, then there's researcher discretion. Which model do I choose? Which output do I want to interpret? Which output do I want to report? That's a problem, right? When the researcher has a lot of discretion, well, we know the consequences of that, right? We know from enormous amount of research in social psychology that we will inadvertently, or perhaps sometimes intentionally, bias things in our own favor. No matter how hard we try, that we're just prone to do that. We're human beings, right? Meaning-making machines, and we just bias things, right? Otherwise, the results of imbalance, model dependence, and researcher discretion leads to this bias. So let's look at that a little more specifically. Even if we had, for example, a whole lot of unbiased estimates, and we make a qualitative choice based on the outcome, that's still a bias estimator. So if we've got, specific example, suppose we choose, we had 15 pristine randomized experiments, right? Perfectly conducted randomized experiments so that everything was done right. Okay, but there are 50 different sets of data randomly drawn from exactly the same population. And every one of those is unbiased, judged ex ante, right, ahead of time. However, suppose we run the 50 experiments and the estimator is the choice of one of them, and we choose one of those based on the results. Let's say it's just the largest result. Okay, what's the consequence of that? Well, the consequence of that is that we have now a biased estimator, right? It's biased answer because it was a qualitative choice. Even though it was from unbiased estimates, it was our qualitative choice from among those unbiased estimates, right? So it's a bias, so it produces a biased estimator. In fact, if you use the social scientist's favorite explanation for why we do things, right? It's plausible. That's what we say. We make our decisions because it's plausible. Well, then it's probably worse, right? That makes it even worse. So whatever kind of judgments we use in those situations to choose among things, that ex ante ahead of time may be unbiased, but nevertheless, using the outcome, we can make it worse. Okay, that's just part of what we do inherently. Well, suppose we put a whole lot of effort into it, and we really try to make it not biased. After all, we're all scientists here, right? We want to make the right decisions. Suppose we just try really hard. We just really try hard. Well, as it happens, conscientious effort doesn't avoid bias. It doesn't work. This is evidence from social psychology where there's quite a lot of really good experiments actually where people try to work very hard to reduce their biases and it just doesn't happen, right? It doesn't work by just trying hard. And the reason why is because people just don't have access to the mental processes to avoid the problem. And there's studies that support that, provide evidence of that. There's always a pattern in our choices and in our behaviors due to the subjective nature of just human decision making. Yes? Not necessarily. I mean, a lot of times the bias is there inadvertently. We don't even realize that we're doing it, right? We think we're, in the example here, right? We've got 50 studies of pristine, unbiased estimates, and we're going to just choose one of them because they're all unbiased, right? So it shouldn't matter. But our process of making the selection really isn't unbiased, right? It's qualitative, and there's always a pattern in our behavior and our decision making. So as best we try, there's still going to be some pattern or system in the decision making process. It could be unintentional. It could be intentional, but generally, I mean, we try to give scientists the benefit of the doubt, right? They're not trying to cheat the system. It just works out that way, right? So there's always this pattern in choices and behaviors just due to the subjective nature of our decision making from even among alternatives, even from among unbiased alternatives. So in order to learn, right, you need feedback. You need some feedback. When you don't have feedback, you're not going to improve. You're not going to know when you're biased. So if you're trying to avoid things that you don't have feedback on, then you're not going to improve. And it's really difficult to know when you're being biased and when you're not being biased, right? So, okay, well, if we take that to the next level, then suppose we have an expert, right? And we have the expert try really hard not to be biased. Well, what happens then? Well, as it turns out, experts tend to overestimate their ability to control their personal biases even more than the non-experts, right? And we have the study from Tetlock in 2005 that demonstrates that for us. So furthermore, even the most prominent experts are the most overconfident, right? The more expert they are, the more confident they are that they can control their own internal biases, and it actually makes the problem worse. So the real problem is all of you and me, right? The experts. We're the real problem. So, but we don't want to take the responsibility for being the problem, right? So suppose we take the experts and we teach them, right? That's what training and education is supposed to do, right? We take the experts and we teach them about the biases that they're likely to create, right? Well, maybe that'll solve the problem. What do you think? Oh, well, we should ask the experts. As it turns out, there's a Nobel Prize winning psychologist, I think probably the only psychologist who's ever won the Nobel Prize, Daniel Kahneman. Right? He got the Nobel Prize for economics, but he was a psychologist. So he did a lot of work in decision making and has written some really interesting stuff. Right? So he makes a comment in a paper that he wrote in 2011 that teaching psychology is mostly a waste of time. I don't think he meant that in general. Right? He's a psychologist, but in this situation, in context of avoiding bias, it's true. Right? You can't avoid bias when there's researcher discretion. Okay, so that's the problem that matching solves. Without matching, you have the imbalance in the model dependence and the researcher discretion and bias. With matching, as we saw in the little demonstration before, right, you get rid of the imbalance. By getting rid of the imbalance, then you eliminate the model dependence, you reduce researcher discretion, and you greatly reduce bias. That's not to say that you completely eliminate it, right? Because we're still human beings and we're still there's still a lot of subjective decision making that goes into research and interpreting findings and things like that. So it's not, we wouldn't go so far as to say that it's completely eliminated, but greatly reduced, right? So one of the most effective ways of dealing with the phenomenon is of the nearly inherent bias in human decision making is through statistical control, right? Statistical matching that we've talked about. So what's the consequence? Well, what's the consequence for statistically controlled matching? Well, with matching, we're going to get rid of the imbalance and we have balance. And then we can reduce the bias. In fact, it goes a long way along with what's been a long-term central project in the field of statistics as a discipline, which is automating away from human discretion, or when possible. It's an interesting kind of balancing act, right? Because we still have these subjective components in the process, but we want to try to reduce our involvement in that as much as possible, just because we know that kind of thing happens. So we want to use as much information as people actually have, but not use the biases and the other kinds of maybe inadvertent things that humans are maybe not so good at, right? So we want to try to rely on more objective information. Okay, so let's get into the details here. This is kind of the background. Well, yeah, that was a separate example. The use of matching is valuable in the context of non-randomized studies. So those were our 15 kind of pristine studies to reduce the bias or the subjective decision making that goes into the choice of those unbiased estimates, rather than just qualitatively choosing one from a list. Right? The way to get away from the bias in that example would be to randomly select the results, right? By randomly selecting the results, then we've avoided the bias in that context, right? The use of matching is when we have a situation where those randomized control trials, randomized experiments are either not possible or not feasible or not ethically appropriate. And we have to rely on then some non-randomized design, right? Then we can use the matching to overcome the challenges and limitations of the design that are inherent in just having those non-equivalent control groups, right? Okay, so in terms of the details of how all this works, I tried to keep, the notation and stuff as simple as and straightforward as possible. So I hope not to get too deep into the weeds here, but feel free to slow me down if I take off too fast. Okay, so what's matching, technically speaking? So in matching, we're going to have a basic setup here in the most simplest possible case. So we've got a dependent variable, y, that's the y sub I, that's the dependent variable. We have a treatment variable, that's the t sub I. I just refers to the individual who receives that treatment, right? That's our key causal variable, and it's going to be a binary just to keep it simple. So just a kind of a yes-no kind of response. And we're going to call the ones the treated and the zeros controls. Actually, the one's not there anymore. So forget I said anything about a one, right? I did in an earlier version. I had in parentheses here a one to indicate that was the treatment group and zero was the control group, and then I just took the one out, right? Just to try to keep it simple. Okay, so let's see. So it could be, the variables in this case, it's just kind of a generic example. So the variables could be anything you want, but it is binary variable. Okay, and then we'll have a whole bunch of pre-treatment confounders or covariates, right? You could think of it in terms of pre-existing profile characteristics, or it could be pre-test or pre-existing health condition, anything that may be an extraneous variable or a confounding variable that could influence the observance of the outcome. Those are going to be the control variables. And those are the X's, right, in the model. So this is the simplest setup that we can generalize this. So the T, or the treatment, in fact, can have more than two categories, right, in studies. You don't have to limit it to just a binary variable, but it's just simpler to present the example that way. It could actually be, in certain cases, it could be continuous variable. We're just going to focus on the simplest case so we can understand what we're doing. So where Y is the dependent variable, T is the treatment, and X is the whole list of the control variables, right, the confounders. So now we're going to look at what's the thing that we want, right? What we want is the treatment effect for the treatment observations, right? The treatment effect, that's the TE. We want that for the treated observations, which is the Y sub I. Those are the treatments, the observed treatments. And so this is the treatment effect, right? The TE is the treatment effect, and the treatment effect is going to be defined as the value of Y if it were treated, right? That's this one, the observed treatment, which is there, minus the value for the person if in fact that person were not treated, right? So that's this one, right? So it's the observed with the treatment minus the value for the person if in fact they were not treated. So the thing about this is that the first person, the first one is the unobserved, the second one is the observed, right? So the treatment effect is the causal effect for that person, and the observed value minus the value that would have been the case if the treatment had not been applied to that person. So obviously that's not observed because it's a treated unit. So what do? What does the matching do is it estimates the unobserved thing with another observation that's very much like the observation that we're studying. In fact, it matches on all of those control variables. We'd like to match it exactly, right? But in a non-randomized kind of study, we can't always do that, right? But so we match it as well as possible, and we take that outcome variable value, which is the Y on the slide here, and we just substituted it in, and that's the way of estimating that treatment effect. So obviously, all of this depends on choosing the correct confounding variables, right? That's, again, part of the researcher's discretion is to identify what those confounding variables are at the outset so that you can control away the effects of any bias from this. And we would not usually estimate the quantity of interest for each person. We'd estimate an average, right? So that's where we're getting at what the quantities of interest are. We would usually estimate an average, so the simple average treatment effect on the treated, that's the SAT, sample average treatment on the treated effect. That's the mean of the treatment effects and the effects over all of the treated units, right? So you could do it all over all of the units, but for matching, this is a convenient way of doing. Sometimes we would also prune, and the spacing is kind of messed up there, but sometimes we'd also prune some of those treated units that are just really badly matched, right? We prune out those units that don't have a good match with the treatment, and we estimate not the sample average treatment on the affected treated, but a feasible SAT, right? Where we prune out the badly matched groups too. It actually changes the quality of interest, but that's okay. It's an observational data analysis. We don't have the randomized assignment to the groups, and that's what we do in observational analysis. So one of the great things then about matching is it's incredibly convenient, right? It's convenient from a data analytics perspective because you don't have to change all the procedures that you have for doing the analysis, because basically what you do is you think of matching as kind of a pre-processing of the data. You take the data and you match it in a very particular way. You prune out some of the observations and it produces a matched data set, right, that you then analyze any way that you were going to before, right? However you're going to analyze it previously. If you're going to run a regression, you can still run a regression. If you want to run a two-stage least squares, you still run your two-stage least squares. If you want to run a big logit, you can run the logit, right? Whatever you want to do. whatever you're going to do previously, it still works, right? It's just it's a pre-processing of the data. That's all. You just pre-process your data with matching, and then you go right ahead. And pruning the non-matches makes the control variables matter less, right? And that's what we saw in that earlier example where we went from the quadratic, right, before the matching, and then we looked at after matching, we get the same findings. So pruning those non-matches makes those control variables matter less. It breaks that link between the treatment variables and all of those X variables. It reduces the imbalance. It reduces the model dependence. It cuts down the researcher discretion that we talked about before, and it eliminates a lot of the bias, right? So another way to think about matching then is it's finding these randomized experiments. They're not really randomized, right? Because we didn't randomly assign participants to groups, but it's a way to think about finding these randomized experiments that are hidden in the observational data just by identifying the matches and then getting rid of everything that doesn't match, right? Ideally, we would love to be able to randomly assign things to different observations, but we know that we can't always do that. So in general, we just think of matching as a way of finding these hidden randomized experiments in observational or non-randomized data. Okay, and so I've listed here different classes of matching, and this is where things start to get a little muddy, perhaps. We get into the details of these different matching protocol. Yes? Yeah, because inherently it's not going to match, right? I mean, by definition, what you have with non-randomized studies is a non-equivalent control group. You don't know. So there are probably going to be some cases in your control group that do match the treatment group on some of those confounding variables, but not all of them will, right? So you've got differences in variability between those two groups, right? So what the matching does is it cleans up some of the within group variability, right? And allows it.
If I don't see any language speaking to they did matching, then their results could be suspect.
That's right.
And I see a lot of the dates are not all that long. They're like 2000.
No, I mean, there's some really recent literature on these approaches, but
So does that mean that they're just not introducing it? Like all the studies before, maybe aren't so trustworthy?
perhaps. I mean, it's not necessarily intentional, but I mean, there is a possibility of the imbalance, right, and the researcher discretion in terms of the models that were used. It's not uncommon to have model misspecification of data. You know, what we're taught in multiple regression courses and even analysis of variance in these research methods and designs is that you always are very intentional about screening the data before you really begin the data analysis, right? You want to look at what are the patterns of the data and the relationships in the data and in the distribution before you start running the analyses, because you never know what might show up, and you may have variables that you think are related in a linear way, right? As one increases, the other increases, or whatever. But it's possible that that's not the true relationship between those variables under certain conditions, right? It may very well be a nonlinear pattern. But if you force fit a linear model, like a linear regression, two-stage least squares, ordinary least squares regression onto nonlinear data, then what you're going to get, even if you're just looking at correlation, right? The results, your output is going to suggest that there's no relationship between those things at all, when in fact, that may just be an artifact of your data. They may be really related significantly, right? Statistically significant relationship between those variables, but because you analyze those data using a linear model, when in fact the pattern of the relationship is nonlinear, you're going to interpret that as non-relationship, right? So that's kind of how that works. Okay, so we've got different approaches or different classes of matching methods. So I'll just kind of go through these very quickly and then talk about some of the implications. So each method here is defined, represents one of the two existing classes of matching methods. So there's the equal percent bias reducing, the EBPR class, and then the monotonic imbalance bounding, MIB class. And so I mentioned in one of the earlier presentations this Mahalanobis distance matching. It's one of the longest standing matching methods that can fall within the EBPR class. And so I cited a couple articles there. There's coarsened exact matching, or CEM. This is a leading example within the monotonic imbalance bonding class. And there's a reference there. And then, of course, the propensity score matching could also be the EPBR if it's used with appropriate data, right? So I think that's where my slides ended. So again, in general, if we think about these matching techniques as a way of finding hidden randomized experiments in non-randomized data, that's the big takeaway, right? The details of how to use these things can get pretty deep into the weeds. But if you think about in the randomized experiment world, right, where we are able to randomly assign participants to groups, we can balance the covariance in that context, right? Whether they're observed or unobserved, we can balance those covariates, an ANCOVA model analysis of covariance or something like that, for example. And you just think of, maybe two of the major experimental design protocols. So we've got completely randomized designs, and then you have blocked designs, right? Randomized block designs. Well, in the completely randomized designs, the balancing of those observed or unobserved covariates averages out, right? The unmeasured variables differ only at random because of the random assignment, right? The random assignment takes care of that. So the unmeasured variables differ only at random, so they average out over time. They're essentially the same, right? We assume that they're the same based on the random assignment. Well, with the randomized block design, on the other hand, the key difference is that since the measured variables, some of the measured variables and the key variables are blocked on exactly the same balance. They have the same balance because we've blocked on those variables. They're not on average, but in your data, because we've blocked on them, right? We've controlled for all those extraneous factors, so we have an exact match in a blocked design. Well, that's in the experimental realm, right, where we can randomly assign things. Well, what happens with these matching techniques is that some of the matching techniques will also kind of follow the same protocol as a randomized block design in experimental methods like the Mahalanobis distance or the coarsened exact matching, right? In those matching approaches, you get the exact match just like you would in a blocked design, a randomized block design in ANOVA, for example. Propensity scores, on the other hand, are more like the completely randomized design. So on average, right, you might get those matches, but for all intents and purposes, the way that the propensity score weighting and the propensity score matching works, it's like a completely randomized design. So on average, you have those matching, but it still allows for some discrepancy. So in some cases, right, it is possible, it's conceivable that once you prune out all of the control variables or the non-matches, then all of the matches are going to be exactly the same, right? And so you don't have the kind of variability that you need to be able to make the comparisons between those groups. In other words, if you have more than two groups, for example, more than two levels of control or more than two levels of the treatment, then it's possible that you're matching controls and treatments at random that are not necessarily the best match, right? It's kind of a lottery approach in terms of how those things are matched up, as opposed to the exact matching protocols and some of the other procedures. So that's the primary limitation of those propensity scores. And I apologize that I don't have the slides to kind of walk us through the steps and make it a little more clear, but all of that disappeared somewhere on Google Drive between working at home and working in the office and the limitations of syncing, right, files. So my apologies for that. But anyway, that's kind of where it ends up. Questions or comments about any of that? Very useful techniques. I don't know if, yeah, go ahead. What you'll see with Ruben's work, and I cited some, referenced Ruben, some of the other presentations, the Mahalanobus distance matching is really good, but it's usually most commonly used by methodologists, right? So it's really good for simulation studies and things like that. But in the real world, in terms of analyzing data in applied kinds of setting, you shouldn't use the Mahalanobus distance. You really want to use the Euclidean distance, right? It's more interpreted, because what Mahalanobus distance does is it standardizes the scores, right? And it kind of takes you away from the meaning of your data. Yeah, right. In multivariate research, we use that a lot. So the recommendation really is if, unless you're doing methodological studies and propensity score theorems and things like that, you probably don't want to use this approach, but rather the coarsened exact matching. So what the coarsened exact matching does is, like in the previous example where we had education as our variable, rather than just treating it as education, right, overall, you would define, you further operationally define that variable, right? So for the education variable, rather than just treating it as education as the variable in general, you would want to have, elementary school versus high school versus college versus graduate professional. That's what the coarsened part of the coarsened matching means. And then essentially you create like a matrix within, if you think of it as a scatter plot where you've got your control groups, individuals scores, and your treatment individual scores as a scatter plot. And by doing the coarsened exact matching, then you can think of it as like a matrix or a grid over your scatter plot, and then you do the matching within those cells of the matrix, right, based on that coarsened exact match. And so that's how that works. And it tends to be much more effective matching procedure than the propensity score approach. And actually, I think we're close to the time anyway, so there we go. Other questions or comments? All right, thanks for your patience and your time.